This is CPE 225. This is lecture 2. We're going to go over partially some memory operations, kind of review what we already know about the RISC-V, and get a quick overview of assembly language, and then we'll do some example problems. So unfortunately, I'm not going to be doing any programming today. That will be the next lecture. So the problem with teaching assembly language is it's really hard to do because so many topics are based on other topics. And so what I'm going to ask you to do is just believe me when I say stuff. Take stuff for granted, and then we'll fill in the details later. The stuff what we're going to talk about is usable without an explanation, but certainly you can use it better if you understand it. And we're going to certainly develop an understanding of what we're doing. So assembly language are essentially it's a bunch of mnemonics, which are just kind of a shorthand notation, which is alpha characters, etc. You'll see these come up in a bit. And essentially what the assembler is going to do, the assembler in this case is a piece of software. It's going to take that text and translate those mnemonics to ones and zeros. So I like assembly language. It's always been my favorite language. Languages or whatever, however you want to say it. It provides a really great overview of the underlying hardware, which is important for, I think, for anyone programming at any level. And it actually, if you know what you're doing, you can actually write programs in assembly language and make your programs run faster. The issue here is that when programs are compiled, it's a computer. The computer does the best it can, or the program does the best it can, but the issue is you as a human can do better. So the bad points of assembly language is that it is architecture dependent. Every piece of hardware you work with, generally speaking, is going to have a different assembly language, and the programs can be long and tedious. So the consolation here is assembly language, it's just a matter of pushing bits around, and when you after you know an assembly language, it's quite easy to learn a second assembly language. I think assembly language is inherently simple. There's only a limited number of instructions. You only get one instructions per line, and because it's so simple, you end up doing the same stuff over and over and over again, and I call these the tricks and the constructs. And programs themselves, a working program is just a conglomeration of all the same stuff that's arranged in an intelligent manner. So the way I think you should do this is learn the tricks. There's not that many of them. Know the instruction set. Not that many instructions. I know 50 sounds like a lot, but it's really not. And write a lot of code, which means practice. So my approach is I'm going to tell you the tricks, primarily with example problems, as you'll see, and then I want you to write code and submit it to me, and I will make comments about that code and help you improve. In general, keep in mind that you are problem solving. You are writing a program such that it solves the problem at hand. Many ways to solve problems, but we're focused on writing programs to solve problems, and particularly, at least in the first part, will be using assembly language. So the first part of solving a problem is to understand the problem. Once you understand the problem, you can generate a path towards a solution, which means design a solution. And in this case, it means either generate some pseudocode or flowchart. So I don't really work much with pseudocode, but I do really like flowcharts. And typically, I use them all the time. Now, you should use them too. I know people don't, but if it's super, super simple, you can get away without using it. But once it gets complicated, you really need to start with a flowchart. And once you have the flowchart, your final, final thing to do is translate that flowchart into an assembly language. Okay, so memory, we don't get too far into it. Computers have all sorts of different types of memory, but they have some large memories, and those large memories are typically used for the program. Remember, a computer executes a stored program, and just generally data. And so the computers, typically you will use ROM and RAM for that, or random access memory, read-only memory, which is issue I don't think we cover in this course. There's other smaller memories on computers, typically registers, that we need to delve into here. Memory in computers have two distinct uses. They all store data. The difference being is how they access that data and typically how they use that data. Not getting too far into this, but memory for us is analogous to an array. Okay, so there's on the right this is a generic memory module, and the important part is, and this is like hardware oriented, to get stuff out of memory, I'm going to have to use some control signals on this one, but more importantly, I need an address. So if you look at this arrow here on the data, it's doubly directed, which means data goes into memory, data comes out of memory. So when I'm putting data into memory, I'm writing memory. When I'm taking data out of memory, I'm reading it. Okay, that's perfectly analogous to an array. When I take data out of the array, when I read data from the array, I'm not changing it, I'm just grabbing it. When I write data to the array, I am changing it. Okay, so arrays typically don't have addresses, but they have indexes. And I know you've seen this one, and the index is perfectly analogous to the address, and we will run into that later in example problems. What we need to know here is about registers. So register is an n-bit storage element, which means it stores n bits of data. Okay, n-bit is data size, and the size of memory in any computer system is dependent upon the system. So RISC-V has a bunch of registers, that general purpose registers, as I call them, that you're going to use, and there's 32 general purpose registers, and they're going to use for various things, but typically it helps you crunch data in this thing. So all this data here is stored in the register file. All these registers are stored in a specific module called the register file. And then I'm gonna point this out to you. We'll refer back to this. Here's the register file sitting right there. And you can see the data widths coming out of this thing are 32 bits, which is kind of the important thing. And the data going into it is 32 bits also. We'll talk more about this later. Okay, so computer, it's a device that reads instructions and executes them, and executes them on the stored hardware. And I want to remind you that the instructions set and the hardware is defined by humans. It's arbitrary. RISC-V is a big computer, all that stuff. It is defined by the instruction set, not the hardware. People read the instruction set, and they generate the hardware that will be used to support that. So yes, the arbitrary. In general, the hardware executes a relatively small number of instructions, but the RISC-V in particular is designed to be a general purpose instruction set, which means it can do anything. It just can't do a lot of things efficiently. So this is our instruction set on the right. This is what the hardware understands, and I'm going to use this instruction set to control this hardware listed in the programming model. And you can see the register file sitting over on the left there. There are 32 general purpose registers that we can use, and we're probably not going to hit that in this lecture, but we'll hit that later. Yes, there it is. This is once again the full hardware, while this right here is the hardware that you have control over via the instruction set. This is the complete computer right here. So you got a new computer. Generally speaking, you got to understand all aspects of it, because you need to program it, and you may need to modify the hardware. I guess that's not a big issue for this class, but it is an important issue. So when you first pick up a new computer, these are the 5 things you look at. We are going to spend most of our time in items 1 and 2, which is the programmer model and the instruction set. We're going to get a little bit into interrupt architecture, not too much. I don't know how much computer science majors need to know that. Memory model is super important, and the I/O architecture is typically important also. We're going to need to get into that because we need to know how to talk to the computer. Once again, these are the 3 levels of programming. The lower level is machine code. And since the machine code is a bunch of ones and zeros, it's the only thing the hardware understands. We're going to be working at the assembly language level, which means we're going to write a text-based program, send it off to a piece of software called the assembler. The assembler is going to interpret what we wrote and generate the ones and zeros, which is the machine code and which is what the computer runs on. Higher level languages are typically, I write a bunch of text, send it off to the compiler. The compiler typically will generate assembly code and machine code, and then the machine code is used to run the computer. So the instruction set are the tools programmers use to control the hardware. There's not really that many instructions, but once again, it's general purpose instructions, so you can do about anything with it, not necessarily do anything efficiently. Instructions themselves are just bits. The assembler is going to look at those instructions and convert them to bits, so you don't really have to worry about bits on this thing. So there is a trade-off that I want you to be aware of. I can design a computer to do anything, but the more instructions I add, the more complex the hardware is going to be. Typically, the slower it's going to run, but it can do things really fast. Fewer instructions, the hardware is simple, but it's going to require more instructions to do the same thing. RISC-V, open source only. It was specified by the instructions, and from the instructions, the hardware is generated. General purpose, does anything, just doesn't do it well, and it's relatively simple. We've gone over a lot of this stuff. So this is an assembly language program. You don't need to know anything about exactly what it's doing because it's not really doing anything. But there's 3 main parts to this program. Anything following a pound sign is a comment. These are your instructions right here. And then what you have over on the left are this, what we have here is this text, which is an assembler directive. It's not an instruction, it's not a comment. We'll talk more about that later. But these are the 3 main types of your program. If you notice, this thing absolutely looks perfect. It's perfectly aligned. This is the way I want you to write your code in this thing. Once again, you don't need to know anything about what this is doing. So there's 3 parts to that. There were comments, there are assembler directives, and assembly code. So the comments are messages to other humans. The directives are messages from the programmer to the assembler, so you do have control over the software a little bit, and the assembly code itself is a message from you, the programmer, to the computer. So there it is once again, not too exciting. So instructions, what do? They do one of 2 things. They do something, or they tell you to go somewhere else and do something. So these are doing something, I don't know, number crunching. Going somewhere else is like a jump or a branch. And included in that jump and a branch is subroutine calls. So a little bit lower level, I'm essentially use all these blocks here. If I'm talking to the computer, I'm going to use the I/O block. If I'm crunching bits, I'm going to use the processor. If I'm storing data or just running programs, I'm going to use the memory. And so those are typical instructions. Also, when I tell the computer to go somewhere else, that's going to be a jump or branch instruction, and we'll hit that a little bit later. So there's 2 types of instructions in RISC-V. There's the real instructions, which I think they call ABI instructions, which I forgot what that is. I think it's application binary interface. I can't remember, but what you want to know is there's real instructions and there's pseudo instructions. So we use both. The assembler is going to see pseudo instructions and convert those to real instructions. The hardware only understands real instructions, but not a big deal. we would typically, we're only going to discuss the details of the real instructions. So this is your programming model again. Over on the left, you can see that there are 32 registers. For right now, we reference those as X0 to X31. Oops, sorry about that. You get that in there. And yeah, there's additionally on the right side is the memory. Typically, as we've been mentioning, that holds the program and it holds data. And later we'll be talking about the stack, which is just another special form of data. These are the types of instructions, basically. Over on the left side, these are the instruction mnemonics, which give you an idea of what they're doing. RET is short for return, which is how I'm going to return from a subroutine, which I call using the call instruction. Call and return happen to be pseudo instructions, not a big deal. The reason I toss this up here is because I'm showing that some instructions have no operands. Some instructions have 1, 2, and 3 operands, and these are the operands sitting right here. We reference these, at least for now. RD is a destination register. RS is a source register, and we'll get into that more later. So this is the 3 levels of instructions that you need to be aware of. So I might write this bottom statement in a higher level language that gets converted to this assembly language statement. You can you see I kind of adding 2 things, and it does the add in assembly language, but you don't really know how it works. Someone has to tell you. So just real briefly, this instruction is going to take the data in register X21, add it to the data in register X22, and store the result in X20. It's kind of had this right to left thing going on, which is kind of unusual, but that's typically the way it's done in computers. The assembler is going to see this add instruction and convert it to 1s and 0s. There's your 1s and 0s. That's hard to read, so we're going to use hexadecimal notation, which I'm going to delineate by the 0x sitting there. If you see a 0x, that's this escape character. It means everything following the 0x is going to be interpreted as a hexadecimal notation. Here's assembly code instruction once again. There's a bunch of different instruction formats. You don't need to get too far into this. This is more of a 233 thing, but you can see that these instructions. The add is an R-type instruction. There's various types of instruction types. It gets converted. The add instruction is right here, and what you see is a bunch of 1s and 0s sitting there. Those are constants. Those are actually the opcodes. That's what the computer uses to figure out which instruction you're doing. These other fields here, which is RD for destination, RS for source, those are your registers. There's 32 registers, which is why there's 5 bits there. I need 5 bits to delineate the registers. So these are field codes as opposed to opcodes, which are the 1s and 0s. Opcodes are constants. Field codes dependent upon the registers you use in the instruction. Yeah, so every instruction has field codes and opcodes. We're not really going to get too far into this. This happens to be a cutout of the R-type instructions. These are a listing of the different types of instructions up here. You can see the opcode listed up there, but obviously what you don't know is the Func3 codes right here. Those are opcodes, and then the Func7 codes are opcodes as well. And then we'll get more into this later. You can see lots of register definitions sitting in there. Not a big deal for now. This is, yes, we already talked about all this. Instructions have field code and opcodes. Opcodes are what the assembler uses to figure out what instruction it is, and then the field codes are what are kind of delineate which registers you're using for those instructions, generally speaking. So that's it. These are just some example problems, so I'm going to step through these real fast. So main components of a computer are going to be I/O, because I need to talk to it. There's a processor, because I'm going to grind bits, and there's a big memory where I'm going to store data and programs. So computers generally store two types of data in memory. That's going to be the program and then just generic data. For us, that means generic data, not typically included in that as a register file. So three types of programming we're going to deal with is machine code, which is a low level, bunch of ones and zeros. What we're going to be looking with is assembly language, which uses mnemonics to give us an idea, us humans, an idea what we're doing. And then there's a higher level language like C or Python or Java. The main purpose of the assembler is to convert assembler is a piece of software. It's going to take your text-based assembly language program and convert that to ones and zeros. And instruction mnemonic is just a shorthand notation for us humans to understand what you're trying to do here. And what the assembler is going to do is read that mnemonic and convert it to assembly language, which for us means field codes and opcodes. That's all, folks.